Welcome back to this course, Advanced Memory Hierarchy Design. In this lesson, I will describe a compiler technique called blocking or tiling that increases the locality of reference by processing subblocks of a matrix instead of entire rows or columns. I will also estimate the effectiveness of blocking using matrix multiplication as an example. Blocking, which is also called tiling by the way, can or should be applied when there are multiple matrices, some of which are accessed along the rows and some of which are accessed along the columns. The classical example is matrix multiplication, x equals y times c. The two outer loops iterate over all elements xij of the product matrix X, and the inner loop with index k computes the dot product of the row I of y and column j of z. This code corresponds to the algebraic definition of matrix multiplication. In this case, loop interchange does not solve the problem we have, since y is accessed along the rows, but z is accessed along its column. The idea behind blocking is to process submatrices or blocks instead of complete rows or columns. If we do so cleverly, we maximize the reuse of data loaded into the cache before it is replaced. Let's look at how blocking can be applied to our matrix multiplication example. When we apply blocking, we should block the two inner loops such that the two inner loops access B times B submatrices. B is called the blocking factor and should be chosen in such a way that a B times B submatrix fits in the cache. Let's look at matrix multiplication to make this more concrete. Here's our matrix multiplication code with the two inner loops highlighted in blue. And here's the code after blocking. Two outer loops with indices jj and kk have been added, and they are incremented with the blocking factor b each iteration. Furthermore, the two inner loops have also been modified. The loop with index j now loops from jj to jj plus b, but when jj plus b is larger than the matrix dimension n, it loops until n. Similarly, the k loop now loops from kk to kk plus b. Blocking improves spatial as well as temporal locality. How? I will try to make clear on the next slide. Now I want to estimate the number of cache misses of matrix multiplication m times m, starting with the original unblocked code shown here. To do so, I will make use of figures such as these ones. In these figures, every square or box corresponds to a matrix element. Furthermore, the colors of the boxes indicate which elements are accessed in a loop. In these examples, the colors indicate that in the inner loop one element of X is accessed, a row of Y is accessed, and a column of Z is accessed. Furthermore, I'm going to focus on compulsory and capacity misses, since conflict misses depend on the organization of the cache as well as the matrix dimension n. Finally, I will make two worst-case assumptions. The first is that a cache block contains only one matrix element, so is 8 bytes in size. The second bad assumption is that one row or column consisting of n doubles or 8n bytes does not fit in the cache. Let's start with the original unblocked matrix multiplication code shown here at the top for ease of reference. First, observe that xij is never reused. It is set once to R and then never reused after that. So assuming we employ right allocate, every access to xij will miss, and this corresponds to n square compulsory misses. Now look at the inner loop. It accesses an entire row of y, then j is incremented, and then the same row of y is reused. By assumption, a row does not fit in the cache. So every row element has been replaced before it is reused. This implies that every access to y misses, And since there are n cube accesses to y, this corresponds to n cube capacity misses. In fact, the first n square accesses are compulsory misses and the remaining accesses are capacity misses, but this is too much detail. Now consider the two inner loops, the J loop and the K loop. It accesses all elements of Z, and then after I is incremented, the first element is reused. If a row is larger than the cache, the matrix Z is surely larger than the cache. So we again conclude that every access to Z misses, and since there are n cube accesses to Z, this corresponds to n cube misses. So in total, unblocked matrix multiplication will incur 2n cube plus n square cache misses. This is quite disastrous since it performs about the same number of floating point operations. Now I want to calculate the number of cache misses of matrix multiplication after blocking, shown here for ease of reference. In this code, I assume that B divides n so that no minimum calculation is needed in the two inner loops. First, let's consider the accesses to the matrix X. This figure illustrates that the two inner loops, highlighted in blue in the code, access an n times n over b submatrix of X. Then the loop index kk, highlighted in green, is incremented, and we access the same submatrix again. So we see that we access an n times n over b submatrix of X before the first element is reused. Since we assume that a row is larger than the cache, the submatrix also does not fit in the cache. So each access to X misses. The number of accesses to X can be calculated by counting the number of loop iterations. The outer loop iterates for n over b iteration. The next loop iterates with index kk also consists of n over b iterations. The loop with index I loops for n iterations, and the loop with index j has b iterations. So there are n over b times n over b times n times b accesses to X, which amounts to n cube over b misses. Now consider the accesses to Y. This figure illustrates that the loop with index j, highlighted in green, repeatedly access a subrow of b elements of row I of the matrix Y. This can also be seen by observing that Y is accessed with the indices I and k is incremented by the inner loop, but I is invariant with respect to the loop with index j, highlighted in green. So the loop with index j repeatedly accesses a subrow of b elements of row I of the matrix Y. The first time this row is accessed, there will be b misses, compulsory misses. Thereafter, every access will hit, since b elements fit in the cache. The outer loop has n over b iterations, the loop with index kk also, and the loop with index I has n iterations. For each of these n cube over b square iterations, there will be b misses. So in total, n cube over b accesses to X will miss. Finally, consider the accesses to Z. This figure illustrates that the two inner loops, highlighted in blue in the code, access a b times b submatrix of C, and then the first element is reused. In other words, the loop with index I, highlighted in green, repeatedly accesses a b times b submatrix of Z. There will be b times b equals b square misses the first iteration of the loop index I. Thereafter, every access will hit, since we assume that a b times b submatrix fits in cache. There are n square over b square iterations of the two outer loops, and in each iteration there will be b square misses. So in total, n square accesses to Z will miss. To summarize, n cube over b accesses to x will miss, n cube accesses to y will miss, and there will be n square cache misses to z. So in total, blocked matrix multiplication incurs 2n cube over b plus n square compulsory and capacity misses. Unblocked matrix multiplication, on the other hand, incurs 2n cube plus n square cache misses. For large n, the first term in both expressions dominates. So effectively, we reduce the number of cache misses by a factor of b. Recall that b should be chosen such that a b times b submatrix fits in the cache. Assuming a 32 kilobyte cache, it can contain 4k doubles. The square root of 4k is 64, so b equals 64 might be a reasonable choice. But the cache should also contain a subrow of b elements, so b equals, let's say, 60 might be a better choice. Anyhow, a reduction of the number of cache misses by a factor of about 60 is significant. This completes this lesson. Thank you for watching. In the next lesson, I will discuss one more compiler technique called loop fusion. Hope to see you back.